Hi, I'm Emre, and this is my CS358 final project. First off, this is what I'll be going over today. Overall, I'll explain what I did and the topics I explored, along with a demo and some concluding thoughts. We'll start with what I explored, along with some details about what made me come to this decision. As we all know, we explored OpenMPI in the world of distributed systems this quarter. And in the past, I've had exposure to these systems, but I never was given the proper toolkit to build one. With our contrast stretching project, I became inspired. I wanted to explore the world of one of the most important CS concepts available, one that companies like Google, Netflix, and Amazon use. But what project would I build or explore? That brought me back to thinking about my main programming language, C++. With my recent switch to it this quarter from Python, I naturally didn't know much about the compilation process. There it was. I could make a distributed system that compiled various programs. After doing some research and seeing that I was confident I could pull it off, I started to dive into the world of distributed compilation. That brought me to Bazel RBE, an open source distributed system compiler made by Google. Now, what truly is Bazel RBE? Let's get into it. Let's start with the basics of compilation. When you compile code, your computer reads source files, pre-processes them by expanding header files and macros and some other stuff, and then compiles that pre-processed code into machine code called object files. The linker takes all these object files and links them to create your final executable. However, for massive projects like Google Chrome with millions of lines of code, this process can take hours on a single machine. Bazel is Google's build system that acts like a smart project manager, analyzing your code dependencies and creating an optimal compilation plan. RBE, remote build execution, takes this much further by distributing your build across Google's cloud infrastructure. Instead of being limited to your laptop's 4 to 8 CPU cores, RBE can simultaneously harness thousands of machines in the cloud to compile different parts of your project in parallel. The magic happens through 3 key innovations. Intelligent caching that only recompiles what actually changed in the project you're trying to compile. Massive parallelization that splits across hundreds of machines. And consistent environments that eliminates the "it works on my machine" problems. The results are dramatic, and because of this, companies like Uber, LinkedIn, and Dropbox use Bazel RBE to transform build times from hours to minutes, reduce hardware costs by up to 70%, and free developers to focus on coding instead of waiting for builds. Essentially, RBE gives you access to a supercomputer for building your code, one that lives in the cloud and scales automatically based on your project needs. Now, how did I go about recreating this? Let me walk you guys through the thought process I followed. Clearly, Bazel RBE is very complex. With support for many programming languages, different compilers, and caching of compiled files, and dynamic job scheduling, this was something that fell outside the scope of this project's resources. A project of this size takes thousands and thousands of devs and hundreds of hours. So I had to find a way to simplify it. The new question became, how can I reproduce Bazel RBE in a doable fashion for me? Now, I'll explain what I built to you guys, what features it has, and what features it lacks. Then, I'll give you a quick demo using the program I built on both a small and a large project. Some features I do have in my program are distributed compiling, load balancing, automatic linking, and error handling. Some features I don't have are incremental building. My project compiles every project it's given from start to end. I don't have good error handling. I just give a yes or no. Did the program succeed or fail? Multi-language support. My program only compiles C code. And finally, cross-platform building, which means my program is hard-coded for my Mac right now. Let's go into the demo. This project is a distributed C compiler built with OpenMPI. Currently, it compiles C projects from start to finish. The coordinator process broadcasts all header files to workers so they can properly pre-process and compile the code, while distributing .c files based on file size using a greedy algorithm that assigns larger files to workers with the smallest current load. Each worker compiles in its own isolated directory to avoid file conflicts and sends the resulting object files back to the main node. The system includes robust error handling. Only if all workers successfully compile their assigned files does the coordinator proceed with linking the object files together to create the final executable. Now, I have two bash scripts here and here, as you can see, that I will use to test and time my solution, comparing to a standard compiler. And then I have two projects here, one more complex with many files, and then one more simple project right here. Here's the code. I'll scroll through it slowly. You can skip ahead to go to the demo, but here is the code if you're interested. Okay, so now I will go into the demo, starting with my first file, my first bash script. Here we go. I'm going to make the terminal bigger, as now we don't need to see this. And as you can see, going to the top, we see that the build completed on the standard compiler in 0.25 seconds, and we outputted the executable. And once again, we did the same thing with our version in 0.33 seconds and got the same output. However, as you can see, because this was the small simple file right here, there's no point for distributing the project. It's the overhead of MPI and creating different processes and sending stuff back and forth is overriding the parallelization benefit. So now I'll go and show you the more complex project on the left here. First, I will delete the output of the program from the last test, but quickly to go through it, you can see that I have workers. They all have .h's. They have their main.c and utils.c that they were assigned, and then the object files which they sent back to main. And if you can check, they have different object files. And yeah, we get all the object files in the main part of the directory, and then it's made into the final executable. So let me just delete all of the code it just gave us so I can run into the next demo without it getting too cluttered. Okay. Now we'll go into the next demo, and we'll go with the more complex project. And as you can see, we have 3 seconds on the normal compiler that did all of these files sequentially, and then we have a 1.39 second time on my distributed system C compiler. So as you can see, we got about a 2 times speed up, maybe a little higher, across using 3 machines, as we launched it with 4 machines total, and we had 1 head process and 3 worker processes. So yeah. Now let's get into some concluding remarks. With OpenMPI creating processes and sending files back and forth between different processes, it causes a lot of delay. Therefore, with smaller projects, it's better to sacrifice the parallelization and just do everything sequentially. However, as you saw with the larger programs, it became very worth it to distribute the compilation process. It's interesting as it shows the real-world use of this project. These compilations can take hours and hours, and we can shave that time off significantly. And on the right here, you see some graphics for some experiments I ran earlier, not in real time. This is from the past, and the results were pretty similar, about 50% to 2x, and then a little bit higher for my rebuild with the small program. Last but not least, here are some of the sources I used to learn about Bazel RBE, including their official website, their repo, as it is an open source project, and some general info for using Bazel RBE. In the future, I plan to continue this project as I had a lot of fun on it, and include some features like incremental building, which means that it won't compile from start to end each time, robust error handling, instead of saying, yes, we succeeded, or no, we failed, it would actually give error messages, and dynamic scheduling to reach an even closer replica. In conclusion, this is just one of the many applications of distributed systems out there, and it goes to show how useful they can be and why so many companies use them. Thank you.